When designing TimberTech buildings for seismic performance, we need to choose the origin of the response spectrum. This can either be a regulation spectrum, which follows building codes and seismic rules for the area, or a user-defined spectrum, tailored by the designer to match specific site conditions or project needs. When we use a regulation spectrum, we're following seismic rules from building codes. To set it up, we choose 4 key things. First, the peak ground acceleration, or PGA. This tells us how strong the ground shaking could be. It's like the earthquake's biggest punch. Second, the importance factor. This shows how critical the building is. A hospital gets a higher score than an office because it must stay safe during a crisis. Third, the soil type. This depends on what's under the building: rock, sand, or clay. Soft soil can make the shaking worse. Last, the spectrum type. This shapes the response spectrum. It could be elastic or adjusted for design, based on what the code says. Let's take London as an example. It's in a low seismicity area, which means earthquakes are rare and usually very weak. According to Eurocode 8, the AGR value, that's the design ground acceleration on firm ground, is typically no more than 0.04 G in places like London. That's very low. So, in simple terms, the ground shaking expected in London is minimal. This makes it a very low seismic risk zone. This graph shows the seismic response spectrum. On the vertical axis, we have spectral acceleration, marked as SE. On the horizontal axis, we have the period, T, in seconds. There are 2 curves. The blue line is for ULS, which means ultimate limit state. The red line is for SLD, or serviceability limit design. At the start, both lines rise quickly. The ULS curve peaks around 0.14 G at about 0.05 seconds. The SLD curve peaks lower, around 6 centimos. This sharp rise shows the strongest shaking for short-period structures. As the period increases, both curves drop. ULS stays higher than SLD, showing it's designed for more critical safety conditions. By the time we reach 4 seconds, both curves are nearly flat, meaning very little acceleration for long-period structures. The damping ratio is set at 5%, with a correction factor of 1.0, so no extra adjustment is made. This chart helps engineers design TimberTech buildings by balancing safety and serviceability based on how the ground is expected to shake. This is the design spectrum for SLV, plotting spectral acceleration, SEG, against period, TS, in seconds. We've got 2 curves, the blue dashed line for ULS elastic with 5% damping, and the solid red line for ULS design. Starting on the left, the ULS elastic curve jumps to about 0.11 G around 0.05 seconds, showing the peak ground shaking for short-period structures. The ULS design curve starts lower, around 0.07 G, reflecting a reduced demand due to the behavior factor. Both curves drop as the period increases. The ULS elastic declines steadily, while the ULS design falls more gradually, staying below it. By 4 seconds, both taper off near zero, indicating minimal acceleration for long-period structures. Key details: regularity in elevation has a coefficient of 1, ductility class is DCL, and the behavior factor Q is 1.5. This chart guides TimberTech building design, balancing elastic response and design safety. For a user-defined spectrum, set the following properties: regularity in elevation indicates structural uniformity, importance class reflects building criticality, e.g., high for hospitals, and ductility class defines deformation capacity, e.g., DCL for ductile structures. Additionally, import the SD, G, VSTS file, which provides spectral displacement, SD, versus period, T, data, covering both serviceability limit state, SLS, spectra, for normal use conditions, and ultimate limit state, ULS, spectra, for maximum safety design. Now, let's talk about the intervention type. We've got 2 options to choose from. First, there's timber construction. This means we're building a new structure from the ground up, using a ground foundation. Second, we have timber vertical addition. This is when we build a new timber extension on top of an existing building. That existing building is called the substructure. For the substructure, we need to decide how it behaves during an earthquake. There are 2 possibilities: a rigid foundation system, which means the base is strong and doesn't move much, or a flexible substructure, which can bend or shift when the ground shakes. If we go with a flexible substructure, we need to give more details. What's the construction type? It could be masonry, steel, or a timber frame. What's the height and number of floors? We need this for both the existing substructure and the new vertical addition. Now that we've finished entering the seismic properties, let's treat that as our default input for now, and move on to the next window, which is wind. In this section, we need to enter the main wind parameters. First, the wind velocity, That's the basic wind speed for the site. Then, the air density, which affects how much pressure the wind applies. And next, the terrain category. There are 5 terrain categories to choose from. Each one represents a different type of surrounding environment, like open fields, suburban areas, or city centers. After that, we'll need to include a few more factors. Orography, which accounts for hills or slopes. Anemography, which relates to wind measurement data. And the size of the structure, which affects how wind loads are applied. Once all that's filled in, just click OK to confirm and move forward. So, thank you for watching. Drop a comment below or email me with any questions. Have a great time ahead.